Hello everyone. As you continue or begin to work through the problem set from section 1.3, a reminder that if you have yet to view the video on the introduction to proof, make sure you do so. It's about 20 minutes. It's going to give you some examples of certain methods and techniques that we may need to use in this problem set. The other thing is make sure you read the text and study their examples. Some are similar to what I did in the video. Others might be just a little bit different. But hopefully I can provide a little bit of supplement to what you might see in the text. Keep in mind that this whole idea of proof is something you just have to practice and get better at. But as always, make sure you let me know if you have any questions so I can kind of push you into the right direction or give a little better explanation than you might see in the text. Today, what I'd like to do is get into some specific examples of using this thing called principle of mathematical induction. Principle of mathematical induction is a theorem, which means it's an if-then statement. And at the time I'm going to post this video, I will also post a quick little handout with an overview of principle of mathematical induction and also another very specific example of how we use this. We know that inductive reasoning is based on looking for a pattern and noticing a pattern and hoping that pattern continues. Proving something continues indefinitely can be tough. So in induction, we really have two parts to the if. That our proposition, or what we think is true for some case, n equals 1, n equals 0, but sometime. And then the other part is, I know that if I can get to one case, I can make the jump to the next case. And then you put those two things together, you can continue to make the jumps forever. My example is that if there are a bunch of rocks across the river, and you know that if you can get to one rock, you can make a jump to the next. And then I get you to one rock, then you can go across the river. There's no problem. So it's those two things together that are the if part of the principle of mathematical induction. Now, the examples that I'm going to show you demonstrate what I hope are even the two possibilities of how we can use this, or how it tends to be used. One is to complete a pattern. So if I have some type of a sequence or a series of things happening, somewhere in my inductive step, I'm just going to add the next term. And when we add the next term, we just combine it with the others, and then we have a statement that we're looking for. The other possibility is, once we show it works for one case, I just consider the next one in terms of substitution of k versus k plus 1. And some of these things are going to make more sense as you read through my example, look at the book, and also watch these. So let's just get into the examples, and then I'm sure I can say a few more things as we talk. This first one is we want to prove that I squared from 1 to n is this big expression. Now, any of you that have taken calculus, this was one of our expressions that we used, or you could use when you're dealing with the exact area under a curve. But I won't even get into that. But it is a statement, and we can show it's true a lot of times, but we want to prove it's always going to continue to be true. So what I can possibly do here is, to start a principle of mathematical induction, I am going to basically I'm just going to call it p sub 1. Okay, in other words, I'm going to let n be 1. And when we do that, we are going to consider from 1 to 1 of I squared. Well, of course, what that's going to be is 1 squared or a 1. There's not much calculation there. All right? Sometimes people would call this the left-hand side. I don't necessarily think you need to, but I know a lot of textbooks will kind of clarify it that way. So that's all of this. Now, the other option, we then put a 1 in for these. And that also equals 1. So we might call that the right-hand side. So we're basically establishing that this is true and n is 1. I could have chosen 2, 3, 4. You might as well start at the beginning. So what that means is this. Therefore, P of 1 is true. So when starting the principle of mathematical induction, we can almost always get to this point, right? Now, the next part gets a little tricky. We have to make an assumption, right? And we're going to assume that it's going to be true for some value. So I like to write the word assume. Sometimes we don't. We could use let. But I'm going to assume pk is true. And what that means is that the sum as I goes from 1 to k of I squared is k times k plus 1 times 2k plus 1 all over 6. So this is that second part. It's going to be the inductive step. It's true for one case. I'm just going to assume it's true at some rock on that river. Then I'm going to show I can jump to the next rock. Now, in order to do this, what I have to do is come up kind of with the next term. All right? Some people would say let. I like the word consider. Let's consider the next term. We could even say k plus 1 term. So I'm going to have 1 squared plus 2 squared plus 3 squared plus dot, 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 all the way to k squared, plus the next term is k plus 1 squared. So I already have it all the way up to k squared. Now I'm just going to have the next one. All of this, of course, by assumption, is this expression. So all of that becomes k times k plus 1 times 2k plus 1 over 6 plus this k plus 1 squared. Now, sometimes we need to pause and kind of ask ourselves, what are we looking for? How do I know when I'm done? Well, basically, here's what I'm hoping for. When I added this extra term, my hope is that I can take this and manipulate it so it looks like this, except wherever there's a k plus 1. So that's the trick. That's the inductive step. Because if I know all of these are now k plus 1s, then I know when I add the next term, this format still holds. So it's always going to be true. It shows that I can go from the k term to the k plus 1 term. And as I said, this is where it gets tricky. Sometimes we can set up the inductive step, but quite often there's some interesting things that happen when dealing with this inductive step. So let me just go through it and see what we end up with. A lot of things I could do. I could expand it, but I probably don't want to. So I'm going to take out a k plus 1 from both these terms. All right, because they happen. So I'm going to write this as k plus 1 times, this is going to be k times 2k plus 1 plus 6 times k plus 1. And all of that is still over 6. All right? Now, if we continue to work with that just a little bit, let's see what might be able to happen inside there. I think I've got k plus 1. This could be a 2k squared. We would then have a k, we'd have a 6k, so we'd plus 7k. Then we have a 6, I believe, all over 6. Now, I'm going to move over to this side here and try to continue that. This hopefully can be factored, right? So this, all of this becomes, I'll just set it here, k plus 1. How about 2k plus 2, and would it be k plus 3 maybe? See if that works. That's going to be 6, 7, 8, so that doesn't quite work, right? So what are our choices? 1 and 6. Okay, let's see what happens. It would be 2k squared, 2 and 7. That's not going to happen. 2 and 3. Okay, so eventually if you can factor it, we'll get to it. I just like to play with it just to show that, eventually you can know how to factor, but hopefully that works. We got 2k squared, we got 6, and we have 7k. Now, believe it or not, we're about done, because now we just have to compare this to what I want. Sometimes I actually write down, what do I want? Well, I want that to be a k plus 1. That's now going to be a k plus 2. If I put a k plus 1 here, that's going to be 2k plus 3. Oh, I have it. But the only way to make it maybe even more obvious is to write this as k plus 1 times 2 times k plus 1. Sorry, I'll do the middle one first. K plus 1 plus 1 times 2 times k plus 1 plus 1. Not really a requirement, but it's nice to see that this and this are the same. So, believe it or not, I'm done. Just still have to come up with some closure, and I'll show you how to do that. Every proof by mathematical induction, we have to say we're using proof by mathematical induction, either at the beginning or sometimes at the end. And here's a way to always write your conclusion. I could say, since P1 is true, because we said what the proposition is, and PK true implies PK plus 1 true, then by the principle of mathematical induction, we could say PMI, PN is true, for all n greater than or equal to 1. And there you go. We have the first case, we establish it. We then have to make an assumption, that's key. Then we have to use this assumption somewhere in our inductive step. In this case, we just created the next term. So that's the way we work with that example. Now, you might need to study it. There are going to be a lot of others like this. The one I give on the extra handout is very similar to this one. So between the two, hopefully you're going to be able to make some sense of it. The second one illustrates kind of the other avenue we can take when dealing with that inductive step. And it is a divisibility one. Divisibility is a cool type of thing because we can prove it a variety of ways. If we would be in a number theory course, we could use it or prove it using mods. And sometimes that's very clean, very short. Proof by mathematical induction is a little bit more elaborate. But let's get started with this one. Again, I'm going to start with my proposition. This would be the proposition. So sometimes people actually rewrite that. I want to call that P of n. My proposition is that 4 to the nth plus 2 is divisible by 3. Now the other thing is we have to make it more workable. So I still want to consider or start with P1. I'm also going to do it just slightly differently than this one because people develop their own style when writing some of these. I like assume, I like consider. Some people say let or other types of things here. But as long as you get the idea across, you'll be okay. So I'm going to let n be 1. So therefore, 4 to the first plus 2 equals 6, and 6 is divisible by 3. Good. Therefore, I could say so, P of 1 is true. I always want to go for that. I like a check mark too. Now we want to go to the next one. So I'm going to assume 4 to the k plus 2 is divisible by 3. But I don't want those words. I want to be able to write that in a more mathematical statement. So I'm going to say it's equal to 3a, where a is an element of the integers. Okay? So that's really what divisibility means. You can write it as 3 times a some integer. And let's consider the k plus 1 term. I'm going to write it differently. Since I started with n, I'm going to say consider n equals k plus 1. So here's what I have. 4 to the k plus 1 plus 2 equals 4 to the k times 4 to the first plus 2. Hard to argue that, because remember, I want to somehow use this. How am I going to use it? Well, here's 4 to the k. 4 to the k I can substitute with 3a minus 2. So that's what 4 to the k times 4 plus 2 would equal. If we play with this a little bit, we get 3a, 12a minus 8 plus 2, which is going to be 12a minus 6, which can be 3 times 4a minus 2. But all of this is an element of the integers. Because if a is an element of the integers, by closure, all of this is. Therefore, pk plus 1 is divisible by 3. So let's track this one again. We start with letting n be 1, see what happens. It's divisible by 3. P1 is true. We can always get those points. Assume that that's true for some general term. We'll call it k. And then in this case, instead of creating the next term by just adding 1 to the previous expressions, we just let n be k, so we substituted k plus 1 where the k was. And then we have to somehow manipulate it using the assumption to get what we're looking for. And since I know I want divisibility, I want 3 times something. That something could be a whole mess of stuff, but as long as it's an integer, we're good. We then have, therefore, pk is divisible by 3. We would still need to have the closure. And again, this closing statement can be used for pretty much everything. I would now put this right here. Since p1 is true, and pk true implies pk plus 1 is true, then by PMI, P of n is true for all n greater than or equal to 1. So those are my 2 samples for principle of mathematical induction. There are several more in the text. There's an extra one on the handout that I'm going to post here shortly. And there's also several in the problem set that you need to work on. If you research a little bit of induction on your own, you will notice that there is something known as strong induction and weak induction. We're not going to really get into that right now. As long as we can attack some of these types of problems by using the principle of mathematical induction, we're hopefully good. The setup, the assumption, knowing what you're looking for, the conclusion, you should all be able to get to that level. The trick, almost all cases, is this inductive step. Sometimes if you would have done something different here, you might have put yourself in a hole you couldn't get out of. Same with this. To know that I'm just going to isolate 4k, not with this 2, and put it over here is helpful. And that's what experience will tell you. So there's principle of mathematical induction, examples. Do your best to read the text, look at this video, look at the handout. Of course, let me know if you have any questions. We'll definitely be talking about this in class when we do meet or remotely. Have a good day.